Actually, it creates problem to accept the request for the participants who are joining right now, and also to remember each and everything that what are the steps. So thank you for that. And first, so first, what I'll do, I'll just you either you can go to File, New, and the New Model, or else you can just directly click onto this option, create a new model. So I am going to this option, create a new model. And similar way, it is going to ask me the hardware product and the settings and the simulation method and time step. So I'm not going to change over here anything. It is required when you are going to design some specific kind of model in respect to hardware. Like if you have any kind of hardware with you for 602 plus or 604, then you can select. Else also a new option has been added to this latest 20 after 2021 version is this virtual hill mode. So if you click onto this version, so that means you are going to design this entire model on simulation purpose. Not you are not going to use for real time. But if you want, you can also change the settings later onwards. So that's not an issue. So I'll go with Hill 402, same simulation method with exact and time step as auto. So the benefit of auto is that if our model is complex, then it will take the best suitable time step. First, it will go attempt for zero point 0.5 microsecond. If it not permits, then it will increase the time step to 1 microsecond in this way, vice versa. Okay. I'll click on next, and then it will ask me for the review. So I'll click on finish. So then it will take a little bit of time to load the library and the blank schematic page. Okay, so now we have this blank schematic page, and at first we are going to develop the electrical part or the plant part for the model, which I was talking about. And actually, we are having this model in three separate trays. So just because the model is too much complex, the controller is also too much complex. So that's why we have segregated this model into 3 days so that we can develop this model properly with exact time. Okay. So first of all, we'll take all the components which we are going to require to develop the plant part or the electrical part. So can anyone tell what are the components I require? Any idea, anyone? What are the components should I drag and drop?
Voltage source, voltage measurement, current measurement,
That's
DFIG simplified induction generators,
yes,
inverters.
yes, 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 yes. The voltage sensors and current sensors are the basic because we require for any model. That's a basic. Okay. So for this model, the correct answer is we require a doubly-fed induction motor, which is going to work as a generator. Okay. And next we require two back-to-back converters, and then we require some measurement components as well as some contactors we require, and voltage source which will act as my grid. So basically we require three-phase voltage source or three-phase grid. Okay. So first, as I had discussed that already, you know that we require a machine which will work as an generating mode. So I'll just go to machines and drag and drop doubly fed induction machine with VPR. This one, doubly fed induction machine with voltage behind reactance. Not this one. This will take. Okay. And then we'll take two converters, three-phase converters will take. So for that, we'll go to this converter section and we'll drag and drop two three-phase converter, which we are going to use as an back-to-back converter. So I'll just drag and drop two three-phase inverter. One. I'm just dragging the components, just placing it roughly. Then I'm going to rotate it or turn it or flip it, whatever is required, I'll do that. Okay. So first I'm going to drag and drop the components which are basically required, and then we'll move forward. So So now what I'll take, I'll go to sources, and from here I'll drag and drop three-phase voltage source, which will act as my. Okay. So the four main components which I require over here for this modeling part is I have taken. First is doubly fed induction machine, voltage behind reactance, two three-phase inverter, and one grid or a three-phase voltage source which will act as my grid. Okay. Now I'm going to take two contactors for changing the mode of operation. So for that, I'll go to contactors and I'll go to ideal contactors, and from here, I'll just drag and drop a triple pole double throw contactor. Okay. It is triple pole double throw contact. Okay. And next, I require a triple pole single throw contact. Now I require some passive component like capacitor, resistor, okay, and then we'll take some measurement blocks for measuring the voltage, current, power, etc. We'll require that. So we'll move serial wise in this way. So let me just close all these things. Now I'll just drag and drop some passive components. So for that, I'll go to passive component section and I'll require a capacitor over here. And then I require a resistor. Okay. And I require inductor and capacitor. So I just make some space over here and place inductor and resistor. Okay. These I'm going to copy and paste. So I'm going to select this, copy and paste. And paste. Okay. Also, I require other contactors. So I just go to contactors once again. I just forgot to take that one. So I'll take single pole, single throw contactor. Yeah, this one, single pole, single throw contactor. So these are the main components which I require. And now I'll move to this measurement side. Okay. So for that, I'll just give you time to do that part. So no need to worry about that. You can do that later onwards. So now I'll go to measurement section, and from here I'll first require a voltage measurement and some current measurement block. So I just drag and drop voltage measurement over here, and I'll require two current measurement, one and two. Okay. And over here I require one voltage measurement. Voltage RMS basically. So I'm just taking voltage RMS. Okay. Now what I'll take 2 meters. So where you will find the meters, you need to go to microgrid, and here you'll find the meter, three-phase. So I'm just dragging and dropping one three-phase meter over here, and the three-phase meter after this back-to-back converter. Okay. And now I require another for the grid side. So I just drag and drop, place over here. And I'll require another three-phase meter. So I just drag and drop and place it. Also, I require a transformer. So for that, what I'll do, I'll just go to this transformer section, and from here, I'll just drag and drop three-phase transformer, two-phase two-winding transformer. Just make the space a little bit. So these are the components I require. So you can just drag and drop and let me know if you're done. So first I have taken a triple pole double throw contactor. Then we have taken this doubly paid induction machine, DBR. Then we have taken one three-phase meter. Then we have taken a three-phase inverter over here. Then we have taken two current measurement, IA1 and IA2. Its name is default, so do not need to worry about the name. Then we have taken a capacitor, a voltage measurement block, and over here we have taken a contactor and a resistor. Here we have taken another three-phase inverter block, meter, three-phase meter, and here we have taken inductance, three inductance and three resistors over here. And then we have taken a contactor, three-phase or triple pole single through contactor. Then we have taken a three-phase meter. Also over here we have taken a three-phase meter. And then we have taken a three-phase two-winding transformer. And here we have taken a three-phase voltage source, which will act as my grid. So drag and drop all this component and let me know when you're done.
Sir, that three-phase meter I'm not getting.
You need to go to this microgrid. First go to microgrid, then you will find this meter option. And from here, we are going to get three-phase meter.
Sir, done.
Okay, so what about everybody? Is it done or should I wait? Okay, I'll wait. Please let me know if you are done.
Sir, done.
Okay. So now what I'll do, I'll just connect the components which I have drag and drop. Also, I'll rotate the components which is required. Okay. And after connecting, and then I'm going to change the name of the components. So first, I'll connect this side. I'll connect this doubly paid induction machine with this contactor. So make sure your connections are proper. Okay. And now I'll connect it with this three-phase meter over here. So I'll place it properly. So this P becomes a straight line, phase B becomes a straight line. And I'll connect this in this. Next comes our three-phase inverter. So I'm going to connect it. Sorry, I need to change, rotate it, flip it first. So I'm going to select it. You can flip it using this option. And I'll connect it. Now, I'll just create some space over here. So I'll place this current measurement blocks properly. And I'm going to rotate this voltage measurement and this capacitor also. Okay. So first I'll connect this capacitor. Then I'm going to connect this voltage measurement block to measure the voltage across it. And then I'm going to rotate this current measurement block and connect. And I'm going to rotate this current measurement block. This. So here I'm going to need some connection. So for that, what you will do, you can just place your cursor over here and press on control, and your junction will be created. So now again press on control and click onto this and connect. Okay.
Sir,
Yes.
sir, what is the use of connecting a current measurement device in parallel?
Yeah.
IA2.
Yeah, actually. It is not for this purpose, it is for connecting over. Okay. So I just rotate this resistor block and this contactor also. I'll give it. So now I'm going to connect with it. Okay. Please let me know till now the connection is done or not.
Done, sir.
Okay. So now I'll just connect this side. So you can just come to this section. Mix up these properly. So now first of all, I'm going to connect this three-phase meter with this converter. And then I'm going to place this resistor and inductor block properly. Okay. And then I'm going to connect. So I just connect with this contactor over there. And similarly, I'm going to connect onto this. Also onto this section, I'm going to connect it. Okay. Now I'll just make some space over here and connect with this meter. And now what I'm going to do, I'm going to turn this, flip this transformer. So I first select and flip this transformer and also this grid. So I'll make some proper spacing and Similarly, I'm going to rotate this voltage RMS measurement block and do the test box. Okay. And now what I'll do, I'll just take this three-phase meter over here and I'm going to rotate it. And then flip. Okay. So the positive would be on downside and negative would be on the upward side. So I'm just going to connect. Okay. So let me just make this. Yes. So this is your connection.
Sir, which transformer we have used?
We have used three-phase two-winding transformer. Okay.
4 winding.
Three-phase two-winding, not
Yes.
four-winding. This one,
Okay,
three-phase
sir.
two-winding transformer.
Okay.
Last.
Yes.
Please let me know if it is done or not.
Done, sir.
Okay. So I should move forward or I'll wait for the others. Yes, tell me. Should I wait? Participants? No response. Why? Yes or no?
Yes, sir. 1 minute.
Okay.
Sir, move on, please, sir.
I need to wait actually.
Okay.
Done, sir.
Okay. So now I'm going to connect this side, this contacted side. So just and now in this way you need to connect.
Sir, you are connecting in star.
Yes.
Okay.
The this one. Just to mod the circuit a little bit. In this Is it visible properly?
Blur, sir.
Which part I should zoom it out? Because if I want to show the entire schematic, it will be in this one. So I need to zoom some specific part actually. Please let me know tell this part if you're done or not.
Done, sir.
So now what I'll do, I'll just
Done.
name the component which I have drag and drop in the same way, same manner. So first I'll start with this contactor. So I'll just double click on its name and change its name to stator contactor. And this WFET induction machine, I'll change, make its name in shorter form. WFET induction machine, DFIG. Okay. Next, over here, I'll change this meter name as rotor meter. First, this is stator contactor, then DFIG, then rotor meter. I'll hide this name for the converter by right click onto it, show and hide name. This one also, right click, show and hide name. And I'll change the name for this capacitor as CDC. This voltage measurement as V bus. This current measurement as I bus, and this current measurement as I chopper. Next, I'm going to change the name for this contactor as chopper. And this contactor, I'll change its name as R chopper. So first, I
The
have changed.
contactor register. This.
This is the register. For register, I have named it as R chopper, and for this contactor, I have named it as chopper. Okay. So stator contactor, DFIG, rotor meter. I have hidden the name for this converter. Then I have changed the name for the capacitor as CDC. Then voltage measurement as V bus, current measurement as I bus, this current measurement as I chopper. Then I have changed the name for the contactor as chopper, and then for the resistor as R chopper. Okay. Now I'll change the name for this three-phase meter as grid side meter, or I'll make it as grid converter meter. I'll hide the name for this inductor and resistor, so I'm going to select it, right click onto it, show and hide. Okay. Now I'm going to make it as S1 instead of S2, and this three-phase meter as grid meter. This one as grid meter and this one as wind and meter. This would be my VRMS underscore grid. And over here is my VSM. So I've done the naming part. So from here I started CTC, P-bus, I-bus, I-chopper, R-chopper, then for this contactor chopper. This is my grid connected converter meter. I've hidden the name for this inductor and the resistor. This one I have taken as S1 and this one as grid meter. This one as wind plant meter. Transformer I have not changed its name. Here I have taken as VRMS underscore grid, and this is as VS. Okay. So please let me know if you are done up till now.
Yes, sir. Done.
Yes, sir.
Okay. So now I have changed the name for all the components. Now we'll do the parameter part. We'll provide the parameter and enable the voltage measurement block which we require. Okay. So let's start same in the same direction with this stator contactor. So I'll double click onto it. Here I'm going to change its parameter. So I'm going to change this control source to model and feedback output as true. Okay. First as model and then feedback output as true. Then in initial state, I'm going to change the initial state to S2. First, in general, you need to change the control source to model because we are not performing CHIL. So we require to control this contractor using this signal processing part developed in this model itself. Okay. So here you need to select.
Sir, please explain what is the difference between this model and the digital inputs.
I have
Different-
explained it once.
Okay.
If you remember in the converter section, there we have explained it many times actually, but still I'll explain you. There you have seen the control option as digital inputs per switch, digital input per leg, if you remember, internal modulator and model. So when we select digital input per switch, that means from the outside, through the digital inputs pin of the simulator, we need to give the PWM signals for the switches individually. But when we are selecting digital input per leg, then we are giving it pins for the each leg. We're giving it to the digital input pins, similar way. Okay. And then we are having this internal modulator option where the carrier is already inbuilt. We need to provide only reference signal. But when we are selecting the model in converter, not over here, in converter, then we are controlling the switches individually using both carrier as well as the reference signal. Okay. So this is for the converter. But here in this contactor, we have these two options. One is digital input, another one is digital model. So if you select digital input, here you can see SA. SA is the switch representation for this contactor. Okay. So here you need to select in which pins you are providing the switching signal, which is coming from outside through the external controller, not inside it you are designing. So if you want to design it inside the software, then you need to select this option model, and if you click on OK, you'll get an option over here to provide the control logic to this contactor. I think it's clear now.
Yes, sir.
Any confusion? So please let me know. Okay.
Okay, sir.
Okay. So now I'll move to this DFIG. I'll double click onto it. Here I'll just change it as RS.
Sir,
R.
sir,
Yes.
initial state. Sir, for stator contactor.
Yes,
So
yes,
the
yes, yes.
initial
Yes, yes.
state.
First, you need to change the control source to model and feedback output to true, and in
True.
initial state as S2.
Initial.
And in timing, please check it is 0 and 0 for both. Initial state only is from S1 to S2 you need to change. Okay.
So for timing.
Timing both would be 0.
Okay, sir.
Okay.
Sir, S2 means is it, that's normally open for now?
Yes, 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 yes.
Okay.
So next I'll move to parameterize this DFIG. So here I'll just rename it only
Sir?
with this. Yes.
Sir, will you explain plant working of plant part?
We will explain. So let me just complete the model, complete each and everything. We'll explain. Also, there is a theory class which is going to be happen on from 4 to 5 today itself. So you are going to get the idea for that. Okay.
Okay, sir. And sir, in another core coupling, how we connected, we directly bypass, means there was only two connection, no, sir, in last core coupling.
Last core coupling means I didn't get your point.
In the at the end of this circuit, there is another core coupling. So it has only no coupling. Sorry, sir. I thought there is. Sir,
Yes.
here we use two.
Yes. Tell me.
Sir, in the model practice model, it was given, so I said like that.
If
Sir,
you
actually we are using two inverters which have weight 3, and we didn't use a core coupling component.
Sir.
Yes,
sir.
I know we need to use core coupling, but if I means give you the explanation right over here, then it will make hodgepodge. So everything I am making it schedule, so no need to worry about that. I'll place core coupling, and I'll explain. I'll explain why I placed core coupling and where to place coupling. What is the purpose of it? So no need to worry about that.
Okay, sir.
Okay, sir.
Whatever I demonstrate over here, there is some purpose behind it. So no need to worry about it. So we are going to get to know that why I have ignored this core coupling right now, and when I am going to connect. So it is core coupling is basically we used to do in last part, means when we know that it calculate the weight, and then we compile, and then we'll analyze it that where we require the core coupling. Okay, so no need to worry about that. Just follow me, the follow steps which I am doing, then uh, see the example model. Okay, so I was in DFIG. Should I continue or anything you need an explanation?
Continue, sir.
Okay, so here you need to just declare a variable as rs here as an rr. Same, whatever is defined over here, you need to define it in this manner. Capital L, small l, and s. And you need to write over here LLR, and over here as LM, and M as U. So in this way, you need to define. Is it done up till now?
M is equal to
We have represented it as U
U. Okay.
because we are going to use M for another variable declaration. That's why. Okay. So now we'll move to the next step, which is mechanical. Here we are going to represent PMS as P, and this one will make a star, and JM as capital J, friction coefficient as 0, and unconstant mechanical angle as dissolved. Is it okay? Should I move forward?
Yes, sir.
Okay. So then we go to load side, and here it is given as SCADA or external. Okay. So in case of SCADA external, basically we are going to use load source as model because we are going to control this machine over here in the software. We are going to model it. So that's why we have selected the load source or model. So whenever we are designing the control for the components in the software itself, we are going to select load source as model. So that's why we have selected load source as model and load type as dot. So after that, we'll go to feedback. Feedback, we are not going to change anything. It's internal 5e plus 3. This encoder protocol here, we basically, can anyone tell me what is the purpose of encoder? Why we require encoder? Anyone?
For speed measurement.
Basically, we use for position measurement for the motors. So to read that particular data from the actual machines, we have this option, absolute encoder protocol. Here you will find various protocol like ENDAT, BISS. So you need to select if your encoder is coming from outside. Encoder signals are coming from outside, from the actual machines. Okay. So that's the purpose of leaving it over here as an absolute encoder protocol. Next, we'll move to advanced. Here we'll make it as same. We will not make any change. And here in snubber, we are going to change it as infinity, INF. And in output, we are going to enable this mechanical speed and mechanical angle. Okay, and execution rate, we are going to make it as TS. So we have enabled in output section as mechanical speed and angle, and execution rate we have written as TS. Okay. Done up till now.
Sir,
Yes.
so once again, load and feedback.
Okay. Load, I have taken load source as model and load type as torque. And in feedback, no changes there, nothing. Only I have made change on electrical, mechanical. I have defined load on model and torque. Feedback, no change. Advanced, no change. Snubber, I have changed it to infinity. And output here, over here, I have taken extrusion rate as TS. And mechanical speed, I have enabled it and enabled the mechanical angle. Okay.
Okay, sir.
So I'll click on OK. And from here, you are getting the option to provide the torque to this machine. And here you are getting two outputs. One is speed and another one is angle. Okay. Is it clear to everyone?
Yes, sir.
So now what I'll do, I'll take a bus joint and connect it over here and separate it out. So for that, I'll just take a bus, not bus joint, actually bus feed, sorry, means demux. I'm going to take a demux and I'm going to connect it over here. And I'll connect two go-to blocks. So I'll just take two go-to block. I'll hide its name and change the tag as mechanical speed, mechanical underscore speed, and scope as logo. Okay. So this is my speed coming from output one, first output, and I require another go-to block, which is my angle. So I can copy it from here and paste it. Correct. And only I need to change, instead of speed, I'll make it as angle. And I'm going to connect with this. Because we are getting two outputs from this DFIG, right? We have selected from here outputs. First is mechanical speed and the second one is mechanical angle. So here I have connected a bus split to means here we are having one port. If we enable all these ports in this manner, so if I enable the electrical torque, then from this output port I am going to get electrical torque, and from the second one I am going to get mechanical speed. But here I have disabled it and only enabled the speed and angle. So that's the reason if I use a bus split, then I'll first get mechanical speed on output, and then out one port I'll get mechanical angle. And if you want to take all this output, here you need to configure the bus split for the number of outputs you have selected. Okay. From here you will get only one, but you need to split it out. Is it clear to everyone?
Yes, sir.
Yes, sir.
So please let me know if you are done. This part is done. Then we'll move forward.
So it is done.
Okay. So now I'll just configure this rotor meter actually, no, not motor. So here I'll just remove snubber. I do not require the snubber. And this settings would be same. Here I'll change the extrusion rate to TS. That's it. I'll change only the extrusion rate to TS. And I require only this current signals, current measurement over here. So it's already enabled. Okay. Only thing I have changed over here, I have clicked onto this remove snubbers and execution rate from 100 e to the power -6 to TS. Okay. I'll click on OK.
Sir, some warnings appear after
Yeah,
this.
it's not an issue. You just hide it. So from here, I'm getting the current as well as I'm getting a voltage also. Yeah, only voltage and current I'm getting, but I require the current, okay, from this output code. So again, I need to use a split. But here, instead of split, I am going to use a dedicated block, which you'll find in microgrid, and a meter. And here you'll find this meter split. Okay. So I'm going to connect with this one, the output to this input part, and from here I require only the currents. So for that, I'm just going to click onto it. So I'm going to click onto it, disable this voltage, and I require the current. So I just click onto it, IA, IB, and IC. I'm going to enable it and click on. So from here, I'm getting the currents, IA, IB, and IC.
So we click on phase voltage measurement also or not?
It's not required because
So-
we require the currents only. Yes.
So we just remove that one. No?
Yeah, we can remove that one, but as we have taken the meter split, so it is a property. Whatever we require, we can select over here. If we require power,
Okay.
then you can click onto it and okay, then we'll get the power from here directly. So whatever the signals are selected on the meter, it's not an issue. Whatever we select on this meter split, it will appear over here. Okay.
Okay.
That's the advantage of it. Whether in bus split, we need to select it manually. Okay.
Yes, sir.
So now what we'll do, we'll just combine these three currents in one form. So for that, we'll require a bus join. So I'll just type bus join, drag and drop. And here we are getting three currents, so we require 3 ports. So I'll double click onto bus join, change the number of inputs to 3, and run it.
Sir, what is the benefit of using first meter split then bus joint? Because almost they are doing the same thing. First we are just taking an output from this meter, then demux it, and then again mux it to form the same. So what is the benefit of doing this?
See, if we place over here, okay, whatever the output we are getting over here, if we just connect it, if you take this current, directly we enable the current, we remove all these things. Like this way, we remove all these things and we require only the current. And if I click on OK, but it will create some issue over here. There will be some error. So that's why we require a meter split first to split out whatever the signals we require. Then, as we require for our controller part, these 3 signals in combined form. So that's why we are taking a bus join and combining it. That's the purpose. Is it clear or still is there any confusion?
It's clear, sir. Thank you, sir.
Okay. So if I directly connect over here, the go-to block over here directly instead of connecting over here, then it will create some kind of confusion. There would be an error, definitely. Okay. So in that case, what we have done, we have taken a dedicated block which is available. So we have split the signals which we require. Then we connected a bus join and we combined the currents. Okay. In some case, what we require the voltages also. So we can place this meter split, we enable the voltage signals. Then we take another bus join separately to combine the voltage signal and combine the current signals. Okay. So that's the need.
So this rotor meter will measure voltage and current and power. All
Yes,
things
yes,
together.
it can measure, but
you are only
the
taking current.
the
That's why
currents,
you
yes.
use the split.
Yes,
Because
exactly.
we want only current. That's why we are using this split. No?
Exactly.
Okay, thank you.
Exactly. That's the purpose. Because for controller part, we require only the currents. So that's why I have taken meter split and then bus join for this current. Okay. So now I'll require another go-to block. So either we can copy it from here or we can just take a go-to block. So I can just copy it from here and paste it, and I'll just change the name. Tag name. Okay. So I'm going to change its name as RSC underscore IABC. This is the name. I'll just show you. RSC rotor site IABC. Rotor site converter IABC underscore IABC. Okay. Is it done up till now? Hello.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So I'll just connect with it and I'll make a subsystem. So for making a subsystem, just select this part. Okay, select whatever part you want to make a subsystem and then right click onto it and select this option, create subsystem from selection. Okay. So now subsystem is created. We'll just go back to our root. Yes, subsystem. I'll just make it in proper way. Okay. To utilize the space and I'll hide it because we need to give the switching signals to this converter over here. That's why I've done. Okay. So first I have selected the two component and then I have created a subsystem of it and then I have placed it properly over here. Okay. Now next thing what I'll do, I'll just double click onto this converter and change this control to internal modulator, and here I'm going to define this carrier frequency as FSW, and then I'll change the dead time period to 1 microsecond, and it will be remaining with the same, like reference signal -1 to 1 will be same. Only thing I have changed is this carrier frequency as FSW and dead time period as 1 microsecond. Okay. So I'll click on OK, and here you will find the ports for giving the signal to this converter over here. Okay. So now I'll next move forward to this capacitor side. I'll just change its name, change the parameter over inside it as C bus. I'll name it as C bus and click on OK. And here for this voltage measurement, I'll just double click onto it, go to signal processing and enable its signal output. And similarly, I'll change section rate to TS. First, what I have done, I have changed the value for this capacitor as C bus, and then for this voltage measurement V bus over here, I'll just double click onto it, go to signal processing, enable its signal output, and change the section rate to TS. Okay. And I'll click on OK, and here you will get the output port over here. Okay. So from here, I'm getting this V bus signal. So I'll just connect a go-to block over here. I'll just drag and drop a signal go-to over here, rotate it, and connect it. I'll hide its name. And change its tag to V bus. And all scope would be global. So I'll make it global. So I've changed its tag as V bus and scope as global. So is it done up till
So
now? Yes.
value of capacitance CDC.
C bus.
C bus.
Yeah, capital C, then bus.
Okay, sir.
Yeah. And this voltage measurement as V bus and scope as global. Okay. So I'll click on OK. And next we have this chopper and this chopper resistor over here. So I'll just double click onto this contactor over here, change the control source to model. Okay. And click on OK. So now you will get an option over here to provide the control signal for this contactor. Okay. So we'll give the control signal later. We need to give the control for this motor, then this side contactor, and then inverter, also this inverter, okay, and this chopper also. So we'll do that part later. First, we'll configure this part. Next, what we'll do, we'll just change the value for this resistance over here as RCH. RCH. Okay. Done up till now?
Yes, sir.
So now, similarly, I just configured this converter over here. I'll double click onto it, change the control to internal modulator. Similarly, I'll change the same settings I need to do. I change the carrier frequency to FSW and date time period is 1 microsecond. Okay, and click on OK. So done up till now.
Yes, sir.
Yes, sir.
So the same way I have done for this meter, rotor side meter, you need to do for this grid side meter. Okay, so you need to do the same way. Okay, no issues. Change the action rate to TS, and over here we require it for 10 cycles. So I'll make it 10 and enable the current. Current is already enabled and click on OK. The same way I need to develop a subsystem. I need to take meter split and then
So
a bus
remove
joint.
snubber also.
No, snubber is not. Do not need to require snubber. Okay. There is a specific reason we are going to discuss about it. Why?
Sir,
Yes.
in that subsystem, how do you connect input output port?
Uh,
The subsystem over
here,
rotor meter. Yes,
here
sir.
over.
Yes, sir.
See, first you need to take the same way I have taken over here. First, you need to take first meter split. So you'll just drag and drop a meter split. So I'll just drag and drop a meter split and connect it in this way. The same way I have done for this part. Then you require a bus joint. Okay. So I'll just take a bus joint and place it over here. First, as I require only the current, so I'll just double click onto it, remove the voltages and enable the current IA, IB and IC. And here I require 3, so I'll make change the number of inputs to 3 and click on OK. And connect it. Okay. And now what I'll do, I'll require a go-to block so I can copy it from here and paste it. You can copy it from here or you can copy it from another place also, from this place also. Totally depends upon you. And here I'll change the tag name as TSC underscore IABs and connect. The same way.
Okay, sir. So only after that you create a subsystem of this, no, sir?
Yeah, then I just selected this both and I just right click onto it and create a subsystem from this selection. Okay. So in this way, I've created the subsystem.
Okay, sir. Thank you, sir.
And then I had hidden its name. Let me just zoom to this part. Yeah. Okay. The
Sir,
same way.
one go to tag now.
Yes, go to is required over here. The same way I have done. First, I have
Sir,
taken a yes.
GSC.
Yes, it is GSC underscore IABC, and over here it is RSC underscore IABC. Okay.
Sir, I just copied the same subsystem and go to block and
Yes,
then
yes, you
just
can do
paste it
that.
here
Yes, yes,
and
you can
just
do
change
that.
the name of the go to block. So it will.
Mhm.
Oh yeah, okay, okay. Thank you.
Yeah, it will work. It will. Okay. So done up till now.
Wait, sir.
Yeah.
Sir,
Yes.
sir, in grid converter meter, we are checking only voltage, right?
No, we're checking only currents. We require currents, no? Current from here, no? That's why we have checked the current side. Also in the meter split, we require the current.
Okay.
Sir,
Yes.
can you show us chopper and R chopper?
Yeah. Here I have just enable it as control source as model. Okay. I've changed the control source from digital input to model.
Okay.
And for this register over here, I've changed the value of it as RCH. I've declared it as RCH. Okay.
Okay, thank you, sir.
Yeah. So is it done up till now?
Yes, sir.
Okay. Okay. So save this file and we are going to have a break and from 3:55 onwards, okay, we are going to start from 4 actually, we are going to start the theory session. So I'm going to save this file. So I'll name it as DFIG. So if you have any queries, you can ask and then we'll have a break.
So please explain this circuit. What is happening in the circuit?
We'll explain it later onwards. Let it complete, then we'll explain it completely. Okay. Any other queries from anyone?
So 10-minute break.
Yes. We'll continue from 4. Okay.
Okay, sir.
Hello.
Yes, sir.
Very good afternoon to all the participants. This is Shashank once again, and I think our expert has joined. Sir. Sir. Hello, sir. अभी आपको good afternoon, sir. Hello.
हाँ जी.
Sir, good afternoon. कैसे हैं?
Afternoon.
So, dear participants, we are having eminent faculty, prestigious author of several technically sound books, slavish researcher, and sober and unpretentious person, Dr. S.N. Tripathi, Dr. Saurabh Tripathi, Assistant Professor, Common Institute of Technology, Sultanpur. What I say, actually his work is more devoted towards electric drives, renewable energy and microgrid side. And he's having, a weight of more than 5 books, 20 journals and 40 international conference papers. And he's already completed more than 6 research projects, and there are 2 projects still two projects ongoing, and under his supervision, more than 5 PhD theses, more than 50 PG theses, and more than 70 UG theses already completed. And with his contribution, only the Power and Energy Research Center, known as Center of Excellence, was established at Department of Electrical Engineering, NIT Sultanpur. We would like to present our gratitude to Dr. S.M. Tripathi for accepting our invitation to share his talk on wind energy conversion systems and overview. Sir, welcome you, and thank you for accepting our invitation. And now I request you, please enlighten the participants by your experiences with the wind energy conversion system and microgrids. Thank you, sir.
Thank you, Susank, for such a nice introduction, and welcome all the participants. And before I start my talk, let me share my slides. Now, is it visible to all of you?
Yes, sir.
Yes, sir.
Okay, that's
Yes,
good.
sir.
So, I am Dr. Saurabh Mani Tripathi, and I am working as assistant professor in the Department of Electrical Engineering at Kamala Nehru Institute of Technology, Sultanpur. And this institute is a government-funded institute. And the talk of my today's session is wind energy conversion systems and overview. So I will just emphasize over the basic fundamentals of the wind energy conversion system, not very fundamental, that you have already learned in your non-conventional energy resources course. So I will just cover all those things that will comprise of the fundamentals, the power converter topologies, the basic control strategies, and what are the research trends. Then what are the basic concepts for real-time implementation, and some sample results. And at last, I will give the introduction of my Center of Excellence. So let's start. So before I start my talk, let me introduce what basically a power system is. Basically, most of you people are knowing very well that what basically a power system is. So the power that is originating at the power generating plant, it is distributed to the residential, commercial, and industrial customers through various transmission lines and substations. So this structure that you are now seeing on your slide is this is a typical structure, and you may say this is what is called a power system. And a typical power system that can be considered as an analogy with a tree, that the roots of a tree that can be considered as the source of water, which is provided to different parts of a tree. So just like in our power system, the main generating station which supplies the voltage and current to different parts of the power system, the entire power system is classified into generation, transmission, distribution, and ultimately the power utilization. So the roots can be taken as the analogous to the main generating station. And likewise, you may see the trunk, that is the sub-transmission lines. Then again, different parts of the tree, they are the secondary sub-transmission lines, and then primary distribution lines and secondary distribution lines, and ultimately the leaves of a tree, they can be analogous to the end consumers. So entire power system can be just considered as an analogy with a tree. So you people may just consider that how big a power system is, but in a typical sense, a power system can be analogous to a tree, where the roots are providing the water to different parts of the tree. So this is as a whole can be termed as a tree of electricity. Now, basically, I have to emphasize over the wind energy conversion system. So before I start wind energy conversion, let us see how the electricity is generated. So electricity generation is based on the very fundamental principle, that is the Faraday's law of electromagnetic induction, where the Faraday law states when relative motion exists between a conductor and a magnetic field, there will be an induced EMF in the conductor. Here you can see there is a magnetic field, and here is there is a conductor, but there is no relative motion, so the induced EMF in the conductor is 0. Now, when we move either this conductor or this magnetic field, there will be an EMF induced in the conductor, and that will be displayed by this galvanometer. So how the electricity is produced at different points, you must see how the coil positions are, how is the coil positions and how the electricity is being produced. So a typical alternating cycle is displayed over here, where you can see how the electricity is being generated when the conductor is moving in the in a magnetic field. So this is the basic concept that you have already learned in your electrical machine courses. Now coming to the renewable power generation. So as far as the renewable power generation is concerned, we already know that these renewable energy resources such as solar, wind, tidal, these are gaining importance nowadays, and this they are just gaining their importance because of their less damaging environmental influences. And nowadays the wind energy technology is the most emerging renewable energy technology. So over you may see that over the past few decades, the capacities of the wind turbine units have increased from a few tens of kilowatt power capacity to today's megawatt level. So anyway, if you are working on either you are working on solar or wind energy, but the researchers are motivated to work with the aim of maximization of the solar or wind energy extraction and injection of the quality power into the power grid. So basically two objectives are there which needs to be fulfilled, and the researchers are just working on these two areas, how we can maximize the power that is generated from the solar energy system or that is captured from the wind by the wind turbines, and how we can inject quality power into the power grid. So these two objectives must be fulfilled when we are working, we are researching on any renewable power generation like solar or wind. So in wind turbines, what is wind? Basically, a question is, what is wind? Wind is nothing but that is the moving air. You may see in the slide that hot air is rising and then it blows, then it cools off. Then this cycle continues and continues. So this is how the air blows, and it is known as the wind. This is nothing but this is the moving air. Earlier, we have already learned in non-conventional energy resources that wind turbine generators, they may operate either as a fixed or variable speed. But in fixed wind turbines, we were using squirrel cage induction generators. And in variable speed wind turbines, we have two concepts. One is doubly fed induction generator and synchronous generators. Nowadays, in permanent magnet synchronous generator. But I am not going to talk about the fixed speed wind generators. Nowadays, most commonly employed wind turbines are variable speed wind turbines. So we will just talk about the variable speed wind turbines. But before we formally discuss about the variable speed wind turbine, let me show you the classifications. There are two wind turbine configurations. One is horizontal axis wind turbine. You may say that the rotation axis is horizontal here, and the another one is vertical axis wind turbine, and you may see that the rotation axis is vertical from the ground. So based on depending upon the axis around which the generator around which the turbine moves is classified as a horizontal axis wind turbine or vertical axis wind turbine. So these are two main configurations for wind turbine. One is horizontal axis wind turbine, commonly known as HAWT, and the second one is vertical axis wind turbine, known as VAWT. As far as the vertical axis wind turbines are concerned, there are different configurations. One is known as Savonius. The second one is called multi-bladed Savonius, then 5 Darius and Delta Darius. Actually, in this wind turbine, you may see this structure. This is basically a Darius rotor, and this is nothing but the Darius classification of the vertical axis wind turbines. And the another classification is Savonius rotor. So there is Savonius and multi-bladed Savonius. And you may see in this particular slide that the wind form that that includes the horizontal axis and vertical axis wind turbines both. These are the vertical axis Darius type rotors, and these are the horizontal axis wind turbines you may see in this slide. So this is the physical motivation how a wind farm looks like. Now coming to the variable axis wind turbines, so there are two main configurations. As I have already stated, one is based on the doubly fed induction generator that probably you have been delivered a lecture just before this session. That was probably based on the doubly fed induction generator. So one is doubly fed induction generator, and the second one is permanent magnet synchronous generator. When you compare these variable speed wind turbines from the fixed speed wind turbines, you may see that variable speed wind turbines can extract maximum power from the wind at different wind speeds, and therefore these turbines reduces the mechanical stress on the wind turbine by absorbing the wind power fluctuations. So these two configurations can be utilized in variable speed wind turbines, and you can see that in both these configurations you may see that there are two back-to-back converters. One is called in DFIG configuration, one is called the rotor side converter, which is just close to the rotor of the machine. And the second one is called LSC or GSC. This is the line side converter or grid side converter that is connected to the grid. And these two converters are connected back to back. And there must be a bidirectional power flow in between these two converters. So in DFIG configuration, the stator is directly connected to the grid and the rotor is connected to the grid through a back-to-back converter. One is known as RSC, that is the rotor side converter, and the second one is called line side converter. And in between there is a capacitor, that is the DC link. Similarly, in PMSG based wind turbines, you may see there is also a back-to-back converter scheme. One is called MSC, that is machine side converter, and the second one is GSC or LSC, whatever you want to say. That is connected to the grid, and there is an intermediate DC stage in between. It might be an inductor or a capacitor. If there is an inductor, it may be configured as a current source converter based wind turbine, and if there is a capacitor, it is usually termed as a voltage source converter based turbines. So AC to DC converters, these are one of the best topologies for wind energy conversion system in realization of two major objectives. The one is maximum power extraction, that is maximum power point tracking, and the second one is feeding the grid with the high quality of electricity. As I have already stated, there are two main objectives. One is power maximization, and the second one is power quality improvement. So in DFIG based wind energy conversion system, the stator is directly connected to the power grid, as I have already stated, but you may see that there is a partial scale power converter. Partial scale power converter means only a part of the power, only the rotor power, or you may say the slip power. The slip power is to be transferred from the machine to the grid. So this power is usually all about typically not more than 30% of the rated power of the DFIG. So whatever converter that you require over here, that should be rated all about 30% of the rated capacity. So that's why the name is partial scale power converter. So you need not to deploy full rating converters over here. But in PMSG configuration, you may see the machine is not directly connected to the grid, but whole power that is being generated by the PMSG is being transferred to the grid through the back-to-back conversion sim. So this back-to-back converter configuration must withstand with the rated power of the permanent magnet synchronous generator. So that's why this configuration is called full-scale power converter, and this configuration is termed as partial scale power conversion. So and the simple meaning is that if you are using the reduced capacity of the power converters, then you require less cost. And when you are using a full-scale power converter, then you require you have to invest more cost. So this is the only disadvantage of the PMSG-based wind energy conversion system, that you need full-scale power converters that requires more cost for its implementation. But in DFIG system, the partial scale power converters are used, so somewhat the cost is lower. But one advantage of the PMSG-based wind energy conversion system is that the complete the machine is not directly connected to the grid, but it is connected through the back-to-back converter. So a complete decoupling of the wind turbine is possible in this particular configuration. As you may see, complete decoupling means when there occurs a fault at the grid side, there will be no effect on the machine side converter operation. And if there occurs a fault on the machine side converter, then its effect will not affect the operation of the grid side converter. So the operation of the machine side converter and grid side converters, they are mutually decoupled from each other. So a complete decoupling can be established in PMSG in full scale power converter configuration, but it is not possible in DFIG based power conversion power system. So the low voltage ride through capability, that is much more complex in DFIG based system. Rather in PMSG based system, it is more simpler to implement. So this is these are the relative advantages and disadvantages between the DFIG and PMSG based wind energy converter. One major advantage and disadvantage is the use of full scale power converter configuration and the partial scale power converter configuration. Now coming to let's see different power converter configurations, and we will discuss on the PMSG based wind energy in this particular wind turbine system. What are the possible power topologies, power converter topologies that are utilized, that are employed in PMSG based wind energy conversion system. Likewise, except this diode rectifier and boost converter topology, all other configurations that I will discuss, they can be utilized in DFIG based configuration as well. So one configuration is in machine side converter, you may use the diode rectifier and boost converter, and the grid side converter is as it is, there is no change. So in intermediate DC stage, we have the boost converter, and in machine side, instead of using machine side converter, we are using just diode rectifier. So the diode rectifier that converts the AC that is being generated by the PMSG into the DC, and the DC is being boosted by the boost converter, and this the boost converter that is responsible for the maximum power extraction. How this maximum power extraction, what is the philosophy between philosophy of a maximum power conversion extraction, that I will discuss in just after 2 or 3 slides. Sorry. And another configuration, you may see in MSC we are utilizing the back PWM converters, and in GSC we again we are using PWM converters. So back-to-back converters can be utilized. So this is another configuration where back-to-back converter can be utilized as a full-scale power converter topology. Next configuration is using the diode rectifier, and in intermediate DC stage we are just using the jet source network. And this configuration, this jet source network and GSC, this implements a jet source inverter configuration where the shoot-through stage can be overcome. Another configuration is multi-level converter. So for high power configuration, high power wind turbines, we can use multi-level converters. So different topologies are also there in multi-level converters. We can have neutral point clamp converter, flying capacitor converter, and cascade edge bridge converters, etc. So there are multiple power converter topologies that can be utilized as a multi-level converter. So there are different and one thing that is worth noticeable, that in all these configurations we have two-stage conversion. One is AC to DC and then DC to AC conversion. The inverter is responsible for converting the DC power, the DC power into the AC power that will be that is supposed to be injected into the power grid. So these configurations are two-stage conversion process, but there are some configurations, they are single stage conversion. That means AC is being converted into the AC, into the required voltage level and required frequency level. So one configuration is, one power topology is matrix converter, where the variable frequency AC is being converted into the fixed frequency and stable voltage by using the matrix converter. And another configuration that is least reported, I think in some conference paper it has been reported, 9-switch AC to AC converter topology. So this is another topology which is a single stage conversion, and the advantage of 9-switch AC to AC converter topology is that only 9 switches are employed in comparison to the back-to-back converter topology, where you require 12 switches for their implementation. So there are 12 switches in back-to-back conversion topology, but the counts of switches reduces in 9-switch AC to AC converter topology. This is the biggest advantage in this particular configuration. So these two configurations can be termed as the single stage conversion. So many researchers have also investigated on these two converter topologies as well. I will show you the statistics. The power converter topology, these are some statistics how the researchers investigated different power converter topologies that are employed in PMSG based energy conversion system. I am not claiming that this statistics is related to the DFIG system as well, but I just claim that this statistic that I am showing in this slide, this is related with the PMSG based energy conversion system. So you may see that the diode rectifier based topology has been the diode rectifier based topology and two-level voltage source converter based topology. These are the most research topologies among all researchers that have been published in major journals. And the remaining topologies, that is current source converter based topology, that has been investigated by some researchers. Then other converter topology, jet source inverter topology, and multi-level converter. Multi-level converter topology is now gaining importance nowadays, because we are just going to install megawatt level wind turbines. So multi-level converter topologies are being attracted by the researchers. So, and when we are just we are concerned about the single stage conversion, then there are matrix converter topology and 9-switch AC to AC converter. As I have already stated, the 9-switch AC to AC converter topologies are the least research topology. So there is a scope. If any researcher, any student, any scholar wants to further research how the 9-switch AC to AC topology can be best utilized for the wind energy conversion system, that will be benefited for the wind power industry. So this is the typical statistics for power converter topology that have been utilized for the PMSG based wind energy conversion system. And when you compare the mainstream power converter topology, there are certain features. There are a number of converter topology features where the requirement of fully controlled switches, circuit configuration, cost, control complexity, waveform quality, harmonic distortion, switching losses, and conduction loss. These are the most important features. When you adopt any topology, you have to take care of the switching losses and conduction losses, and overall the reliability, bidirectional power flow. And since we are just moving on the concept of microgrid and smart grids, etc., where different sort of renewable energy sources are being integrated with each other, so hybrid operation of renewable sources are possible with these topologies or not, that is also a major concern, major feature which must be taken into consideration while you are choosing a suitable topology for your research work. So these are the comparisons. So again, just looking at the DFIG and PMSG based wind energy conversion systems. So I have already stated that the machine side converter, there are two converters. One is machine side converter, or the in DFIG based system, that is the rotor side converter, and the second one is load side line side converter, that is grid side converter. So these two converters are controlled independently, and they have to fulfill some major objectives. Primarily, the machine side converter or rotor side converter in DFIG based system, the basic objective is to fulfill the maximum power point tracking and control of rotary speed. The maximum power point tracking that can be established by controlling the rotary speed. So how this can be accomplished, just let us see. Let me tell you how maximum power extraction is possible with the wind turbine by controlling the rotary speed. So in this slide, you may see the lambda versus CP graph. Lambda is called the tip speed ratio of the wind turbine, and CP is called the power coefficient of the wind turbine that you have already learned in your non-conventional energy resources course. And here, this is the expression for the mechanical power developed by the wind turbine. Actually, the power extracted from the wind is 0.5 rho. Rho is the air density, A is the swept area of the rotor, and V omega is the wind speed. So the wind and the power that is being captured from the wind by the turbine is 0.5 rho A V omega Q. But CP is the power coefficient, because any turbine cannot be 100% efficient. Basically, the efficiency that is of any wind turbine is limited by its bed's limit. That states that no turbine can generate power. No turbine can deliver power to the generator that is more than 59.3% of the total captured power from the wind. So this is the bed's limit, and this is the ideal one. Basically, in practical, in real world applications, the practical turbines, they are having the efficiency of up to 49% or 48%. Likewise, so CP is a power coefficient that designates how much power is being converted. That can be supplied to the generator from the power that has been captured from the wind. So this is the expression 0.5 rho CP A V omega Q. So in order to maximize the power, you have to maximize the CP. And when you see the lambda versus CP graph, you may see for a single lambda, for only a single lambda, there is a single point which is maximum. So what you have to do, you have to keep the tip speed ratio of the turbine to such a point so that the power captured from the turbine is maximum. That means the CP is having its maximum value. When CP is having maximum value, then power captured by the power generated by the turbine at that particular wind speed will be maximum. This concept can be more easily understood by saying the turbine power characteristic. You may see in y-axis, you may see the turbine output power, and on the x-axis, you may see turbine speed. So when you may see, and these characteristics, the blue lines, these characteristics are drawn on different wind speeds. At 5 meters per second, you may see that this is the characteristic, and this is the relationship between the turbine output power and the turbine speed. At 7 meters per second, this one is, and 9 meters per second, the curve variation is like this, and at 11 meters per second, the variation of the curve is like this one. So for each curve, you may see there is a maximum power point, and all maximum power points are connected by this red line. You may see this is the maximum power point at 11 meters per second. This is maximum power point at 9 meters per second. This is the maximum power point at 7 meters per second, and this one is a 5 meters per second. So let us see how can you control the rotor speed, the turbine speed, so as to achieve the maximum power. Let us see, let's take an example. Suppose your turbine is working at this operating point. At this operating point, the power is in between 0.5 and 0.6. So that means about 50 or 55% of the rated power is being generated, being delivered by the wind turbine. At what speed? The speed is at 0.82 or 0.83 per unit. That means 83% of the rated rotor speed. Suppose this is the power which is being generated by the wind turbine is at rotor speed 0.82 per unit. This corresponds to the 9 meters per second. But suddenly, let us see when suddenly the wind speed changes, because you can't say that wind speed is constant throughout. The wind is intermittent in nature. Sometimes its speed reduces, sometimes its speed increases, sometimes it is steady. So there is an regular changes in the wind speed. So what you have to do? You have to extract the maximum power from the wind by keeping the rotor speed corresponding to the maximum power point. So at this particular point, when the wind turbine is extracting maximum power point, and suddenly the wind speed changes to the 11 meters per second, what will happen? This operating point will shift to this point, and this point is not a maximum power point. So what you have to do? You have to increase your rotor speed so as to achieve this particular power point. What will you do? You will increase your rotor speed, and as you go on increasing your rotor speed, you will reach at this particular power point, which is maximum corresponding to the 11 meters per second. Now suppose suddenly the wind speed reduces to 9 meters per second again. What will happen? This operating point, where this operating point shifts to this particular point. Now at this particular point, this is again not a maximum power point. What you have to do? Now your consideration is, now your objective is to reach at this particular operating point. How will you reach? You have to reduce your rotor speed. So you have to reduce. When you reduce your rotor speed at this particular point, then you will achieve the maximum power point corresponding to the 9 meters per second. So what you have to do? You have to control the speed of the generator, or you may see the speed of the turbine, so as to extract the maximum power from the wind, for which the two objectives: one is maximum power point extraction, and the maximum power point extraction can be accomplished by varying the rotor speed, and which is corresponding to the different wind speeds. Sometimes wind speed is low, then you have to seek the maximum power point corresponding to that particular wind speed. Sometimes the wind speed is high, then you have to act accordingly. So this is the concept how we move on to extract maximum power from the wind. And this is decided, this can be easily understood by this turbine power characteristic. And each turbine, not necessarily this this particular turbine power characteristic, not for every wind turbine. Each wind turbine has some has its own generic equations, so the wind turbine power characteristic changes for each turbine. So this is not a this is a typical curve, not a universal curve. But you may see that the power variation will will be likewise. So there are many techniques for maximum power point tracking or maximum power extraction. Some are the classical techniques. The most employed techniques are optimal torque control, that is being utilized by our industry. Tip speed ratio control, where you need an anemometer for measuring the wind speed. Some techniques utilize the optimum relationship based control, where 1 or 2 parameters or 3 parameters are being observed, and accordingly a control action is performed so as to achieve the maximum power extraction. And one concept is perturb observe, or this is also known as hill climb search. This is another technique which is being most researched by the researchers nowadays. So optimum based relationship control and perturb and observe are the combination of these two. They are most research concepts nowadays. And the class, as far as the classical maximum power tracking strategies are concerned, then tip speed ratio control and optimal torque control, they are best utilized by the industries and by the researchers. So this is the statistics of maximum power point tracking that corresponds to the PMSG based wind energy conversion systems. And different MPPT methods they have been compared in this particular slide against different MPPT algorithm features, which comprises the requirement of wind speed sensor. As you may see, the tip speed ratio requires the wind speed sensor, but rest methods don't require the wind speed sensor. And there is soft speed sensor, lookup table requirement, memory requirement, complexity, cost, convergence speed. Convergence speed is major criteria that you have to take care of, and the oscillation at MPP. Basically, when you track the maximum power point very slowly, then the speed of achieving maximum power is very low. And when you fast track the maximum power point, then there will be some oscillation at the steady state point. So you have to maintain the speed efficiency trade-off. Otherwise, when you your convergence speed is more, the oscillations will be more, and when oscillations is less, the convergence speed may be slow. So these are two parameters, and you have to make a trade-off between these two parameters. Then MPPT efficiency, reprogramming, performance under rapid wind conditional parameter sensitivity, and online updating. These are certain features against which these MPPT methods are being compared. Now, coming to the control strategies, basically we are using the power converters. So for their switching, we have to adopt some suitable control strategy. And basically for machine side converter, we have two control strategies. One is the field oriented control strategy, and the second one is called direct torque control strategy. Direct torque control, in which the torque is directly being controlled. You need not to include the current loop and the inner current control loop. But in field oriented control, you require an internal current control loop. This is an implementation of hysteresis based current controller. So we have two ideas. Either you use field oriented control or direct torque control. Mainly for small wind turbines, we generally prefer direct torque control, and for small, medium, and higher wind turbine, we may use field oriented control. both the strategies have their relative advantages and disadvantages. There are some advantages of direct torque control, some advantages of field-oriented control, some advantages that are associated with the field-oriented, and some I will compare on the table. Let's see how a field-oriented control strategy using a hysteresis-based controller is implemented for a PMSG-based wind energy conversion system. So in this particular slide, you may see that the anemometer here, TP speed ratio control may be utilized. The anemometer that measures the wind speed, that is given to the MPPT algorithm, that is TP speed ratio, and that produces the reference speed. Because I have already said, when you have to extract maximum power, you have to control the speed of the generator. So here the objective is to control the speed here, and this is the reference speed of the turbine. So we have, and the MPPT algorithm tells us how what will be the reference speed of the generator. So that reference speed is being compared by its actual speed, and the error that is generated, that will be processed by some outer controller. Here we are using a PI based controller. You may use another. There are many other controllers, many other advanced controllers. So any controller, any regulator that you find suitable, you may use. And this PI controller processes this error between the reference speed and the actual wind, actual turbine speed, and generates the reference torque. The reference torque, because this is in this particular control scheme, we have just used surface mounted PMSG. So the torque is again being converted into the Q-axis reference current by using a gain, which is mathematically, which can mathematically be established how this torque reference is being converted using a gain into Q-axis reference current. But when you are using interior permanent magnet generator, most of the control strategies directly process the speed error into the Q-axis reference current. So you may tune the PI control in such a way that the output of this PI controller will be the Q-axis reference current. Now, there are certain control schemes for PMSG-based permanent magnet synchronous machines. So here we have just used maximum torque per ampere control, for which we have just maintained that D-axis current component is equal to 0. Now DQ-axis component, which are the reference values, these reference values are converted into the ABC reference frame, and these reference ABC current are being compared from the actual three-phase currents of the generator, and they are processed by the hysteresis current control, which produces the switching signals for the machine side converter. So this is a very fundamental strategy of field-oriented control, which can be utilized for the permanent magnet synchronous generator control. Another scheme is where you may utilize the PI controls in inner loop also. So that strategy has not been included in this presentation, but you may also see in different research papers that PI-based current controllers can also be employed in the inner current control loop. Now, talking about the second converter, that is the grid side converter or grid interface converter. So grid side converter, you may see in DFIG and PMSG, in both the configurations, the grid side converter is directly connected to the power grid. So this is an essential part for the integration of the distributed generator units like wind turbine, photovoltaic. So whatever configuration that you are using, either DFIG or PMSG or solar photovoltaic, so you need a grid interface converter so as to connect the renewable generation source to the grid. So what will be the basic objectives of this grid tied converter or grid interface converter? So there are 5 objectives that a grid tied inverter should fulfill. One is the control of active power, which is generated by the renewable energy resource, which is being supplied to the grid. You have to control the active power. In addition, you have to control the reactive power transfer, because in case of a grid fault, when there occurs a fault, voltage will go down. So in order to maintain the voltage, you have to support the reactive power to the grid. So reactive power control capability is a must. You have to control the reactive power transfer. So this is another objective. You have to control the active power, you have to control the reactive power. And I have already stated, whatever power you are supplying to the grid should be high quality power. That means you have to ensure the high quality of the injected power. High quality of injected power, that means the TSD should be low. The total harmonic distortions should be low, should be as per the IEEE standard. And when you are connecting any renewable resources, any generating unit to the grid, you have to ensure the grid synchronization. Because you have already learned in your machine course that when a generator is being connected to the infinite bus, you have to maintain, you have to synchronize the voltage, frequency, and the phase sequence. So grid synchronization is another objective that a grid type inverter should fulfill. And the last one is control of DC capacitor voltage, because you have already observed that the power that is being generated by the wind turbine, that is AC power, that is of variable frequency, which is first converted from AC to DC. DC has zero frequency, and again this DC power is being converted into AC at fixed voltage level of the that is equal to the grid voltage and at constant frequency. Suppose you are integrating your wind turbine in India, then you have to synchronize, you have to maintain the frequency at 50 Hertz. So in between there is a DC link capacitor. You have to maintain the DC link capacitor. If you are not maintaining the DC link capacitor, then the power that is being supplied by the turbine, that will increase the voltage of the DC link capacitor. So you have to control, you will maintain the DC capacitor voltage. Then in the incoming power that is being that is coming from the renewable resource, that will be transferred to the, that will be pumped to the grid. So you have to maintain the DC capacitor voltage as well. Now you may see out of these 5 control objectives, at a time, using any control scheme, at a time you may fulfill the control of active power, control of reactive power, ensure high quality of injected power, and grid synchronization. Either you perform these 4 objectives, or you may perform control of DC capacitor voltage, grid synchronization, ensure high quality of injected power, and control of reactive power transfer. Either you perform last 4 objectives or you perform first 4 objectives. Because when you perform control of active power generated to the grid, the DC capacitor voltage is indirectly controlled. And when you implement your control strategy in such a way that control of the DC capacitor voltage is being controlled, then you control the active power generated to the grid. You may indirectly control the active power transfer to the grid. So out of these 5 objectives, at a time you may fulfill either first 4 or last 4. Now when we talk about the machine side converter control methodology, there are mainly, I have already told you that field oriented control and direct torque control strategies are there. One control strategy that has recently been reported by some researchers, that is direct current vector control strategy, and that's why the research percentage is 5.71. That strategy shows that only a few researchers have opted this sort of control strategy. But you may see that field-oriented control strategy, that is the most research concept, most research control strategy for PMSG-based wind energy conversion systems. And in a similar way, when you talk about the grid side control strategies, because I have already told you that there are major objectives that the grid side converter has to be fulfilled, has to fulfill. So in this particular control strategy, you may see that we are just showing two control strategies. One is voltage-oriented control strategy that is just similar to the field-oriented control strategy for the machine side converter. And the second one is direct power control strategy. And that is somewhat similar, somewhat analogous to the direct power control of the machine side converter set control strategy. So it is interesting that in first category, in first strategy, which is the voltage-oriented control strategy, we have we are controlling the voltage DC link voltage VDC. So in this particular control strategy, the DC link voltage will be controlled, grid synchronization will be maintained, grid synchronization will be maintained, the power quality will be maintained, and the reactive power support. Reactive power support can be established by changing the reference value of the Q axis current component. Here, IQG is equal to 0 is taken, and this ensures the unity power factor operation of the grid side converter. So by changing the value of IQG reference or by utilizing another outer loop for the Q axis component, you may control the reactive power as well. So in first strategy, you may see that DC link voltage is being controlled and active power is being controlled indirectly. But in direct power control strategy that is shown over here, we are just controlling the active power, the reactive power, and the grid synchronization will be there. That is a must. And the fourth objective, that is the quality power that you have to maintain. So these are the two basic control strategies that are mostly employed for the grid tied converters. So how a voltage-oriented control strategy is implemented in PMSG-based wind control, that have already been demonstrated in last slide. So I'm skipping. In GSC control methodologies, again, voltage-oriented control strategy is the most research concept, then direct power control, and some researchers have now developed the direct current vector control strategy for grid side converter control as well. So there is a scope. You may further research on direct current vector control strategy and direct power control strategy. But voltage-oriented control strategy is more research concept for the PMSG-based wind energy conversion systems. And when you combine the wind turbine, the back-to-back converter, and the grid side converter is being interfaced with the grid, and the voltage-oriented control strategy and field-oriented control strategy, the entire control system looks like what is being demonstrated in this particular slide. So this entire schematic is this belongs to the PMSG-based wind energy conversion system. So where we are just using back-to-back converter, DC link capacitor in between, the grid side converter is being interfaced with the grid, and for grid side converter we are utilizing the voltage-oriented control strategy, and for the machine side converter we are utilizing field-oriented control strategy. So this is the entire control scheme that can be that has been simulated in my work. But different researchers adopt different control strategies, different configurations, different operating conditions. So when you compare the different controls, field-oriented control, direct torque control, and direct current vector control, so there are again different control strategy features, and for against which we compare all these control strategies. Similarly for GSC control strategies. And overall, the status of research for PMSG-based wind energy conversion system, you may see overall most researchers are involved for power converter topologies. Some have investigated for pitch control. The second topmost research is being performed in control of machine side converter and grid side converter stage in machine side converter and grid side converter control area. Then MPPT control. This is again being researched by several researchers. Sensorless control. This is increasingly favored by the wind turbine industry. Sensorless control. Then grid connection issues are also there, which includes the power, the wind power smoothing, reactive power support, low voltage ride through, and different. There are many grid connection issues. They are also being researched by many researchers. So this is the overall status of the research which is being performed in the field of permanent magnet synchronous generator based wind energy conversion system. So when you adopt some configuration, some control scheme, some topology, and you develop your own model, just as I have shown you in my this particular slide, that we have just conceived this particular scheme. So how the real-time validation, as you are just taking the training on the real-time implementation, real-time validation using Typhoon HIL. So what are the concepts for real-time validation? Just let me show you in a few slides. Before discussing this one, let me introduce a typical control system. You have already know that there is some command input, and the actual output is being compared by the command input. Air signal is there, and there is two basic components. One is controller and one is plant. So controller that actuates the plant for producing a desired output. So the output will be controlled by the controller by actuating some signal to the plant. So there are two major components. One is controller, one is plant, and the output is being feedback to the controller by some feedback elements, by some sensors. So this is the this is a typical control system. So in next slide, I will just talk about the controller and plant. So when we are, I use the term plant, that means we are talking about the system which is producing the output, and the controller, that is the system which controls the plant. So one configuration, there are three typical configurations. One is, this is a real-time simulator, HIL 402. You may see, you have already been demonstrated by Mr. Sasank, Mr. Sudipto. When you develop the plant and controller, both in the software, in virtual environment, in software, then this concept is called software in the loop or model in the loop. Basically, the plant and controller both are being simulated in virtual environment. Then this particular concept is called the software in the loop or model in the loop, because the controller model is being developed in the software itself, and the plant model is being developed in the virtual environment. So this is the model in the loop concept. So generally, what you have been demonstrated in the last session, that was the implementation of model in the loop simulation. The second one is when you are using a virtual plant in your real-time simulator, and you are using a real controller. Real controller, that means some industrial controller or some DSP, digital signal controllers, or DSpace, or any other controller that you mostly use in your laboratories. So when you are using a real controller, but the plant, that means your motor, your converter, etc. These are being implemented in virtual environment. And the controller and the real-time simulator are being interfaced in such a way that the plant is being controlled, and controller doesn't understand whether it is dealing with the virtual plant or it is dealing with the real plant. This real-time validation concept or this real-time validation topology is called controller hardware in the loop, where controller is a real hardware, but plant is the virtual one. And the third one is where you use real plant. That means your converter, your motor, your power components, that will be the actual hardware. But your controller is being developed in your real-time simulator. And your developed controller that interacts with the real plant, and the validation, when you validate your entire scheme in this particular topology, this is called rapid control prototyping, where you are using the virtual controller but real plant. So these are three major configurations where you may utilize, you may use for your real-time validation. Another configuration is power hardware in the loop, and that have probably been introduced by Sang. How power hardware in the loop is implemented. Basically, in power hardware in the loop, some part of the physical plant, for some part of the physical plant are actual hardware, and some part of the physical plant is implemented in your virtual environment. And these are implemented by using some power amplifiers, So that is another concept that is known as the power hardware in the loop. So there are different configurations, different concepts for real-time validation. What basically the real-time, what is meaning of the real-time that has already been introduced. I believe that you have been introduced by different experts. So I am not going to explain what basically a real-time environment is. So in our laboratory, we have implemented a real-time simulation setup using Typhoon HIL 402 and display storage oscilloscope. So this is the picture. This is a setup that has been implemented in our lab for implementation of permanent magnet synchronous generator based wind energy conversion system. So you may see this is the real-time simulator 402. This is a breakout board, and this is a display storage oscilloscope, and this simulator is being interfaced, being controlled by this PC. And these are some results of permanent magnet synchronous generator base, because just I was emphasizing over the topologies, control stages. So I am not going to discuss how these results have been produced and what but these are the sample results which are being produced in our lab for permanent magnet synchronous generator based wind energy conversion system, that of which configuration I have shown you in the previous slides. So these are the sample results. Now let me introduce about our lab, our Center of Excellence, that is Power and Energy Research Center. And this center I have founded in our institute in August 2019. And KNIT Sultanpur is one among all government-funded institutions under AKTU Lucknow that is having Typhoon HIL 402 and Typhoon HIL 604 devices. So we have two devices, 402 and 604 models. And as already you know that this real-time simulation environment that extends the real-time simulation and ultra-high fidelity control hardware in the loop simulation facility in dominant areas of powertronics, electrical drives, microgrids, distribution network, and renewable energy, etc. So basically, we have the facility for real-time implementation and control hardware in the loop implementation in our center. In coming few years, we are just planning to implement, to set up the power hardware in the loop simulation facility as well. So basically, we have two experimental setup. One is with 402, 604 real-time simulator and 402 real-time simulator. So experimental setups are there in our center that is dedicated to real-time simulation facility. And whatever I have discussed in this particular session, these are some suggested readings. Now, thank you very much. If you have some queries, you may please ask. Thank you very much.
Thank you, sir. Thank you very much, sir. Participants, if you are having any queries, any doubts, anything you want to ask, please ask. Dictionary of wind energy conversion system is in front of you. You just ask your questions and you will get the answer.
Actually, I have given just 1 hour. I have just given 1 hour for my presentation, so I tried to include all the aspects in a very short presentation. So it might be possible that some of you have not understand the whole concept in a very lucid and comprehensive manner. But for that, I am very sorry. But I have tried to include all the aspects, including from the basic configuration from Savonius and Darius and horizontal axis wind turbine, vertical axis wind turbine, then power converter topologies, control strategies, the statistics.
Sir, there is one query from Mr. Shaurya Sharma.
Yeah.
That is, he's asking about, please discuss a bit about bladeless wind energy system and their viability and comparison. Bladeless wind energy systems and availability and comparison to the conventional wind energy system. Bladeless wind turbine, wind energy systems.
Bladeless.
Yes.
That is new to me. Very frankly, bladeless wind turbines, I have no idea right now.
Mr. Shaur, if I'm not wrong, so this is just means see, as sir told that different types of turbines. So there are one more segment that is called micro turbines. I hope you heard about that. And nowadays, the micro turbines are also used in cogeneration processes. Like if you have seen
But
some of the countries.
Shashank, but that cannot be termed as a bladeless.
No. I'm coming to that, sir. Just give me a second. So some of the countries have installed few micro turbines means on the dividers. So those are kind of means vertical turbines, but their design is a little bit different with the conventional one. So this is just means the idea what I'm getting from your question, Mr. Shaur. Is it related to your question or not? Mr. Shaur? I think he left. Yes, sir. Please correct me. Sir, your voice is. Sir, please correct me. हेलो सर
हाँ आप मुझसे बात कर रहे हैं
yes please correct me
actually I have just searched on Google that there is a concept of vortex bladeless turbines, but this is very new to me, and it is not good to comment on any such topics which is not much known to me. So in this particular question, I just want to make no comments.
No. I'm just means what I answered. Is it
actually your voice was intermittent to me, so I just could not heard your explanation which you given to Mr. Sore.
Okay, participant, if you are having any queries, please ask, and Mr. Shaur will come up on your question maybe by Saturday. I'll discuss with Tripathi sir, and then maybe he will answer, or maybe I'll try to answer your question. Any questions from participant side? Sir,
any question which I have discussed in my session?
So I think there is no questions, no queries. So I like to.
Sir, in
yes.
converter,
yes.
You explained different type of converter and switches.
Okay.
I'm told that single stage conversion in 9 switch and matrix control.
Yes.
And another is 2 to
Two-stage
3
converter.
level, 2-stage converter.
Yes.
Okay, sir.
In basically in two-stage conversion, you have to just convert the AC that is being produced by the wind turbine, that is converted into the DC, and again that DC is converted into the AC. So this is a two-stage conversion process. But in last two configurations, that is the matrix converter and the 9-switch AC to AC conversion, where the AC is being converted into AC. The requirement is for the stage conversion requirement is just because of the intermittent nature of the wind. Because the nature of the wind is intermittent, so the power that is being produced by the wind turbine is fluctuating in nature, and the fluctuating power cannot be injected into the grid by what you have to do, you have to smooth the power, you have to make the power smoothing, and you have to make the frequency constant so that the wind turbine unit can be synchronized with the grid. So this is the major reason why we perform the stage conversion. So some of the researchers, some of the industries are looking at the two-stage conversion process, and recently matrix converter topology have evolved. So they have also researched on matrix conversion for single-stage conversion as well. But the problem of single-stage
in matrix conversion, variable speed AC is converted into fixed AC.
Yeah.
And in also 9-switch AC to AC converter.
Yeah, that may be.
Variable AC comes from wind, is converted into fixed AC.
Exactly.
And fit to the grid.
Exactly.
Yes, thank you, sir.
Anybody else?
Mr. Shaw, he's asking, like, we have known for wind energy plants to be of big farms and spaces. Can they be used in an isolated way? There would be less power, but is there a possibility of research for decreased size and space utilization given the wind is not a problem? Sir, please check in the chat box. You'll get the question. Mr. Shaw, regarding that bladeless wind energy system, I'll add one more term. That is means that bladeless wind turbines work with the vibration, actually, more towards the vibration, and
Mr. Shaw,
right now I'll tell only this thing, and on Saturday I'll discuss in detail about this one.
Mr. Saur, actually, this is not right to state that the wind energy plants can be for big farms and spaces. Basically, nowadays there are many concepts for wind turbines that are utilized for micro generation units. In my PhD, I have also researched on a very small wind turbine that is of rated capacity of 7.68 kilowatts. So this is not a right statement that wind energy plants that can be utilized for big farms only. They can be utilized for our smart homes. Nowadays, there are so smart buildings where the small generators can be utilized in wind energy conversion systems. So in my work, I have utilized the wind generator of 7.68 kilowatt power capacity, and the turbine and the rotor of that turbine was about 2.6 meter. 2.6 meter, that is not very large. So that can be implemented in small spaces as well. And micro wind generation units, if you search on micro wind generation units, you will find more and more results on net. And you may go through, you may pursue on those concepts as well. Thank you. Anybody else?
Any more queries, please?
Can they be decreased to a size and weight like a rooftop solar or similar to it? I have explained that for micro wind turbines where the turbine size, turbine power capacity is less than 5 kilowatt. They are micro, even micro wind turbine concepts are there where you are utilizing a very small capacity generators. So of course, if rotor size is decreased, for example, in my case, we were using a rotor of 2.6 meters. 2.6 meters is not very large. So of course, the size may be decreased, but exactly they can be substituted just like rooftop solar or similar to it. It is a question of, it is an interesting question. Anyway.
Any more queries, please? Sir, I think there is no such queries left. Thank you for giving your sharing your experiences and giving a brief fundamental about the wind energy conversion system. And if any participant having queries, they can mail us or you directly, so that they can be answered by you. So thank you very much, and hopefully we'll have such a technically sound sessions more in future, and you need to be participants. I'll tell you, Tripathi sir is not well, is having fevers, and but still he's able to give his lecture. So it's his kindness. So thank you and have a good day.
Thank you. Thank you, Sushant. So participant, I think we need to end the session now, right now. And one announcement is for you all that you need to prepare a summer training report also. So there need to be 6 chapters, areas on which we are discussing, like power electronics, power system, renewables, microgrid. So each week having their own area. Okay, so you need to prepare your topic accordingly, and you need to add all the models which you have designed, and you need to submit that report, and we'll check that report and then revert back to you, and then you need to submit that report at your institute. I hope so. So there should be 6 chapters, and at last, in conclusion, you need to put your assignments. Already 2 assignments given to you, and in coming days you will get I think 1 or 2 more. Then you need to conclude, you need to finish this summer training report. You need to finish your report before completing this summer training. Okay. So the deadline for this summer training submission of training report is let me check the 1 day prior to the prior to 29. It's the 29th of July. So you need to submit that one up to that day. Is it okay to all of you? Okay. And most of the models we have used, those are available in the example folders. So you can take help from there also. But you don't need, if you are going to copy, we'll understand that, okay, you have copied. You need to develop all the models. What we want, you just complete this training with 1 national certificate and 1 international certificate. Okay. So thank you, and have a good day. Thank you, sir. Good day. Thank you. You don't need to attach the models. You need to take the snapshot of your models, and you need to put that snapshot with results and with SCADA file, with schematic file. Okay.
Okay, sir.
Sir, for some of the models in which we have designed the controller, do we also have to write the steps that are required for designing the controller?
Yes, yes, you need to write everything.
But sir, in some of the examples that are taken from the software, we have not seen that much in detail. The design.
Which one? Which example you are not able to have the not available in the example folder, except the Saturday's model which I have developed.
Okay, sir.
I hope you are having all the models except the Saturday's model which I have discussed with you people for electric vehicle fundamental. So you just include all the models which are available in the example folders. Okay, but don't try to copy that one. So because we can check each and everything. Okay. So good day and bye bye.
Sir.
Yes.
Sir. Actually, I am already